Okay, so now I hope my screen would be visible.
Yes, sir.
Yeah, great. So in forward converter, we were utilizing three turns transformer or three winding transformer, let us say. And here from this figure, we can say that the magnetizing inductance is working to supply the enough current to the secondary side. It is basically helping in, switching, or we cannot have DC switching in inductor circuits or transformers basically operates with alternating currents, but here in isolated DC-DC converters we are utilizing switches to avoid the constant current to the transformer windings. Otherwise our transformers would get saturated and after certain time it will be damaged. So to avoid that, or to help to avoid those conditions, magnetizing inductance help in that perspective. So when this switch was closed, basically this forward converter is working as a our isolated buck converter, right? So its duty ratio, if you see, and if you compare the transfer function of output to input, you will see that V naught by Vs is D times turns ratio of secondary to the primary. And here we were able to observe that tertiary winding was there to maintain the lossless operation of this converter, right? The other solution was to include the lossy circuits like resistance in series with diode, so that whatever energy that magnetizing inductance was storing, that will be lost to the resistor during freewheeling time period. So basically to avoid that, we are using here tertiary transfer tertiary transformer winding. So I hope so far so good. Uh, we started with analysis of this converter when switch was closed and when switch was open, so that we can segregate those operations and we will get the overall better idea, right? So when switch was closed, the voltage appearing across the primary winding was directly Vs, right? Because when switch will be closed, Vs will be appearing directly to the V1 terminal or V1 node, you can say. And once this voltage is appearing at V1, let us call it this node 1. Okay. So, yeah. So, when V1 is appearing at node 1, as soon as transformer winding consisting in two turns, it will see the voltage V1 and the voltage of V1 will get transformed to V2 and V2 will have the value of V1 is to into turns ratio, and turns ratio generally is the ratio to the side we are transferring, right? V1 is here and V2 we are getting at the secondary side. So we multiply V2, we can say V2 is equal to V1 first we will write, and to the side where we are transforming, that turns ratio in numerator we can write, and in denominator we will write the turns ratio from the side where we are coming, right? So let us say this is side 1 and side 2. So we are going to side 2 or secondary of the transformer. So we will write the turns ratio of secondary in numerator, and in denominator we will write the turns ratio of the side from where we are coming, right? Similarly, V3 will also see the voltage, right? It is also connected with V1, and the dot polarity is maintained and it is fixed. Once we have maintained and we are supplying the constant dot polarity, then we should not change it, right? Once we fix the dot polarities in the circuit, it should be fixed, so that otherwise if you keep changing it, if you keep changing the dot polarity in transformers, it will create lots of confusion. So we should avoid doing that. So I was saying that V3 will see the voltage V1, and V1 V3 will again, we can write it as V1 into N3 by N1. However, once the V3 is coming like dot polarity, we are taking positive terminal of voltage always at the dotted terminal. So V3 will have certain voltage and it will come positive, right? Why positive? Could anyone please elaborate it? Why I'm saying that V3 would be polarity with this kind of dotted convention?
Sir, we are measuring the voltage with respect to undotted terminal.
Yeah, from dotted to undotted terminal. So we have fixed our reference of the voltage in such a manner that we are taking positive terminal at the dotted terminal and a negative polarity of the voltage at undotted terminal. So it will be transformed, but the terminal where it is getting transformed, the dotted terminal will always contain the same polarity of voltage what was earlier in the previous winding, or the side of winding from where we are transforming, it will have the same polarity. So when we see that V3 is positive and cathode of the diode D3 is connected to the V3, so it will be reverse biased and the circuit of tertiary winding will be off as long as our switch 1 is closed. Okay. So after that, we computed the blocking capability of diode D3, what it will have. So we applied a KVL along the diode D3. So once you move towards this KVL loop, so you will see that Vs minus V3 plus Vd3 is equal to 0, right? So in that, sorry, Vs plus V3 minus Vd3 is equal to 0. Minus 2 plus, if you are taking the positive convention, then minus 2 plus Vs. So Vs again minus 2 plus V3, so V3, and plus 2 minus, that will be the blocking mode of diode, so it will be minus Vd3. Sorry. Yeah, so this is the
Yes,
polarity,
sir.
so plus
It's correct
Vd3.
only.
Okay, you are saying minus is correct? Yeah, if you are taking
Yes.
this in this way, plus and minus, generally when switch is off, then this kind of polarity we represent, and when switch is on, the left side polarity we represent. So whatever you take, we are concerned with the magnitude only, right? So if you take minus, then you will directly get the blocking capability of diode V3, and that will be Vs plus V3, right? Otherwise, if you take positive like this one from left hand side, if you take, so you will get Vd3 is equal to minus Vs plus Vd3. It means if you are taking this convention, it means you have represented diode as a conductive polarity of voltages, and since during conduction the voltage is appearing negative, it means it won't conduct and it will have to block that much of magnitude. So far so good. Now about this magnetizing inductance, what it is doing. So when switch was on, this magnetizing inductance will also store certain energy, and when switch will get off, our intention is to flow back this energy to the source, right? So when switch is on, we derived it Vs by Lm by the slope of this inductor current, dilm by dt will be equal to Vs by Lm, and during on time period, our T on will be equal to dt. So it is that. And on the secondary side, if you see, we have the voltage V2, which is nothing but the V1 into N2 by N1. Okay. And if this polarity is positive, our D1 will be closed and D2 will be open. And this Lx inductance, similar to our conventional buck converter, right? That is conductive buck converter. And in that circuit, or in this circuit as well, our inductor will be charged during the switch on period. So its slope will be V2 minus V0 divided by Lx. So that's what we have written already. And after that, we plugged in the value of V2 in terms of V1, since V1 is known and V0 will also be known if you know the duty ratio. And after that, we derived that del ILX on has the magnitude of Vs into N2 by N1 minus V0 is into D by FLX. And when you do the del ILX on plus del ILX off is equal to 0, basically it is indirectly a volt second balance equation. And then by this expression you will get the transfer function of voltage of output to the input. And during this condition, the current through switch is flowing, that will be equal to current flowing in the magnetizing inductance plus current flowing in the primary winding of the transformer, right? So here you can see whatever the switch current that has been supplied from the source voltage, that is equal to current going into the magnetizing current plus current going into primary turns, right? Why not current going into tertiary turns?
This diode is reverse biased.
Yeah, because diode is reverse biased, so current won't be allowed in that path. So hence, so it was a very significant observation that tertiary turns is there. Okay, it is connected to our supply voltage conductively as well as inductively. Okay, so voltage will be induced on the tertiary winding as well as if it is connected to the supply, then you will see when switch is off, it will be connected conductively as well. So tertiary winding is quite a flexible path in this circuit. So generally we want that kind of connection which can supply conductive as well as inductive, because many times we see that where magnetics are weak, what I mean to say, when air gap is large enough such that it won't allow the flow of flux efficiently, in those cases we shift to conductive, right? You might have heard about wireless charging, right? So wireless charging of electric vehicles requires inductive operation. Okay, but it is not successful yet. Why it is not successful? Do you have any idea, anyone?
This power transfer is limited, na?
Yes, power transfer is limited. So what is the reason behind that?
The coupling is not effective.
Yeah, yeah.
Yeah. So there also a huge role must be played by magnetics, and magnetics will be effective only there where magnetic circuits are efficient. So generally in wireless charging, your charger and battery will have certain distances, and uh, that will not have enough supply of flux from your supply side where you have chargers installed and to the your vehicle where you have your adapter, or you can say battery is placed. So efficient magnetics are not yet developed. Okay, and you might be surprised at above 2 Tesla or above 2.5 Tesla of magnetic field achievement is kind of huge. People are trying with certain advanced materials like superconducting materials such that so till date the highest magnitude of magnetic flux density is 19.2 Tesla. Okay, so if you go to the Google after this session and if you search
It
that,
is VM, sir.
sorry, BM, yes,
That is
BM,
VM.
BM,
Oh.
Tesla. I am talking
But
about.
we are using here only the 0.25 or something.
Yes. In power electronics, we do not use more. Like it will be limited till 1 or zero point 0.5. So, and in motors, you can go up to 2.5 Tesla or 2.4 Tesla. So it is
But there
limited.
is no material, sir.
So, that is also achieved in advanced material like cobalt steel, right? Generally, we use silicon steel. So in silicon steel, it is limited till 1.8, 1.9 Tesla.
Yes.
If you add cobalt kind of alloy, and that is also limited, and however the cost will rise suit like anything. So uh, but after adding cobalt, some that material name is Vacoflux or Vacoder. If you search in Google after this session, you will be able to observe that its magnetic flux density is up to 2.3, 2.4 Tesla. So generally, power is developed in magnetic circuit based on your magnetic flux density, how much is the magnitude of magnetic flux density into how much is the electric loading, that is current. So if you increase the magnetic flux density in the circuit, you will require very small amount of amperes in that circuit to generate your desirable power. If you have weaker magnetic field, if you cannot afford high or a strong magnetic flux zone, then you will have to compromise on electrical side and you will have to supply higher magnitude of electrical current, and that eventually will create huge copper losses and other losses related to your electrical side. So that's why we want to maintain the balance between electrical, means conductive and inductive side. So that is the one reason behind we are still stuck to the conductive charging. However, in mobile charging, you might have observed that Apple had launched certain inductive charging, that is wireless charging, right? So since our mobile phone has very small amount of battery, its capacity is limited, so it can be charged easily. But once you scale it up on higher level, it will be difficult. So that's what I wanted to clarify here. So moving ahead, uh,
Sir,
yeah, go ahead, please.
sir, in wireless charging, we will usually use a air core type
Yes,
induction, no?
yes, air will be there. Definitely, air will be there. Air core also we generally utilize. So that depends on what kind of constraints you have, what
Yes.
kind of output you want to achieve with what kind of materials and cost. So that depends on your application to application and your constraint to constraints.
So the material is available. Material which provides the which produces the maximum the BM of higher values are available. Only the cost is the limiting factor now.
Yeah, and
Is it, sir?
many people shift to air core. Why? Do you have any idea?
No, sir. I just read
There is
somewhere
no
that.
saturation problem, sir.
Sorry?
There is no saturation problem. There is no loss.
Yes. That is
But
one
you have to
solution.
add the cost. You have to put a lot of ampere turns. That is possible with a superconductor only.
Yes, that is a possible solution, and that is a possible reason. Other reason is that if you insert certain materials like coal, then coal will have certain amount of mass and volume, and you want
Yes.
compact kind of chargers and compact everything is nowadays reducing its size. So you want a smaller and a smaller version of everything. Then you will have to compromise on the material. You will have to eliminate heavier materials and you will try to achieve it with lighter materials. So that's another reason. And at the cost of weight, since you have eliminated the core, then you will have to plug in higher magnitude of current in air core. So that has another advantage that your core will not get saturated, but it will require higher field intensity from your current source. As we will see that our field intensity H we represent, that is equal to Ni by L. So you will require higher field intensity from the supply, and that will be supplied either by increasing number of turns or increasing the current if your length of the core is fixed. So that we will see in magnetic circuit section. Okay.
Okay, sir.
Okay.
This N increases mass and this I increases loss.
Yes, yes.
So,
And you have a limited cross section of material, right? If you are designing anything, you will have limited cross section, and if you will try to incorporate more number of turns than its size, then also it is not possible. So that is another factor. And mmf is anyway, if you want certain kind of magnetomotive force, uh, I think some instability in my pen is arise. So if you see the expression of MMF, what kind of magnetomotive force that can be generated, that is N into I. So it is up to you how much MMF you want by which parameter. So if you have limited constraint on current, then you can increase the number of turns and you can get the desirable MMF. Otherwise, you can increase the current as well with lesser number of turns, right? So it's up to you.
So this N increases the inductance also.
Yeah, yeah,
So
and
this
and
that
increase.
will response time will increase.
Yeah, response time will increase, and size of supply will also increase. I mean, if you have
Yeah.
certain supply, then if you are incorporating higher value of inductance, then your power factor will eventually poor. So
Yes, sir.
yeah,
Sir, here what is LX? LM is
LX.
magnetizing inductance.
Yeah, LX is your inductance that is connected to the load. So if you have studied buck
Okay, okay.
converter, it is similar to the buck
Yes, yes.
converter. It is storing
Okay,
the
okay.
current during the charging period, and it is releasing its current during to the load during discharging current.
Yes.
Yeah. So yeah, so let's see what happens when switch was open. So when we open the switch, let me remove this switch. Yeah. So now once you open the switch, now your tertiary winding is connected conductively to the supply, right? And it will induce the same amount of magnitude of the supply voltage as Vs. However, its terminal will be reversed. So when its terminal will be reversed, you will see that your diode is getting forward biased, and now whatever the energy was stored in this LM, that will flow through the V1, and it will come to the it will be induced to the your tertiary winding. So I3, if you see, I3 will be equal to ILM into N3 by N1. So we are not writing I3 is equal to minus ILM. You any confusion in this point? Because it is a really subtle point. So you need to understand this I1 and I3. The relationship between I1 and I3 is turns ratio. Okay, it is not conductive; it is inductive.
sir, the current I3 is uh, it is N1 by N3 into I1, right?
Yes, yes.
Uh,
I3 is equal to ILM into N1 by N3. It is not I3 and ILM is not connected conductively. That's what I meant. Okay.
yeah.
Yeah. So this current will go back to the source and it will supply back its energy, whatever stored in your magnetizing inductance. Okay. Once it happens, in secondary side, if you see, it will induce the voltage of Vs into what I mean V3 into N2 by N3, right? So let us see here from this circuit, from original circuit. Once V3 has the magnitude of Vs in this manner, okay, and this voltage, uh, yeah, thank you. So this voltage will have the magnitude Vs and it will get induced to the V2 terminal, and V2 will have the voltage that is Vs into N2 by N3, and that value will have the negative kind of polarity. So this diode will get off and this diode D2 will turn on. Okay, and once this diode D2 will be turned on, so earlier this inductor was getting charged from the fact that V2 was greater than V0 and inductor was getting charged. Now V2 is 0 here, if you see from this node, or VD2, you can say VD2 is 0 during this operation, and Lx will be discharged across its load, and during this period we can see that ILX is having certain kind of slope during charging. That was when switch was on, and its slope was V2 minus V0 by Lx, and when it is discharging its slope is minus V0 by Lx. Okay, so this inductor Lx that is connected towards load side, that might be in continuous conduction mode or in discontinuous conduction mode, but the inductor which is magnetizing inductor, that must be discontinuous conduction mode. So this ILM or this LM must operate in discontinuous conduction mode. Okay, why I am saying this LM must conduct in DCM mode? Do you have any idea of this?
because it should it should not have any energy at the end of the cycle,
Yeah,
because it
if
is a
it will,
transformer.
yes, you are correct. If it will have some certain energy at the end of the cycle, then what will happen?
Then it will the current will rise from there in the next cycle.
Correct,
Uh,
correct. That's perfect
so
answer. Yeah, go ahead, please.
with successive cycles, there is a chance of saturation.
Yeah, it will come at a certain point. After that, it will enter into saturation region, right? And once it will enter into saturation region, then it will start drawing huge, enormous amount of current. So that we should always avoid. Yeah.
Sir,
So, hmm,
sir,
yeah, go ahead, please.
but this current ILM,
Huh,
mm, both the starting and the ending,
huh,
suppose both at 0 and at t,
huh.
it can have some minimum value. So if it does stay,
Somewhat value. Could you please repeat that point?
actually here in this ILM at t equal to 0, it is at 0,
Hmm.
it is increasing to dt,
Hmm.
and then at t naught it is coming again to 0.
Yes.
Sir, similarly at 0 it can have some minimum value, it can increase at dt, it can go to some maximum value, and then again at t naught it can come to the same minimum value
Huh.
where it is.
Then what does it mean? You are
Yeah.
saying what he is saying. Let me rewrite it. He is saying that ILM should have certain this kind of waveform. Am I right?
Yes, sir.
And after T naught, what is happening?
T naught, it will remain at 0.
No, at T naught, you are saying that it will have the similar value from where it has started.
Mm, yeah, yeah. It's a no, sir. Actually, we are having a DCM here.
Yeah, that's what I said that we are having DCM here. So in
Mhm.
DCM, what happens in a steady state? It starts from zero and it ends to zero before the starting of of the next cycle, right?
Yes.
Yeah. So let me tell you
Sir,
what happens.
suppose we are in CCM.
Huh? Suppose
Sir,
ILM
suppose
is
we are in,
CCM, yeah.
so we are starting at some minimum value. The current is starting at some minimum value.
Some minimum value, yeah.
Yeah, and at dt it is increasing.
Huh?
Yeah, and again at t it
Huh?
comes to the same minimum value.
Same minimum value. T, at T
At
you
t,
are saying, okay.
yes, at t it's coming to the same minimum value.
Huh?
So if this one repeats, then
Huh?
the 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 core won't saturate. No, sir.
No, see,
So
yeah, yeah, go ahead. You are saying that
sir,
if it will keep happening,
at every cycle, yeah.
then your core won't be saturated, right?
Yes, sir.
So that you are saying. So does
So,
anyone else have this kind of answer?
sir, if but in transformer they say at every cycle the current should reach zero.
Hmm. Yes,
Uh,
yes.
why they are saying sir, that there is a bit of confusion actually,
Okay, okay,
because
okay.
basically in India, suppose if in LX we usually have this kind of waveforms,
Uh-huh.
in the above circuit, in the buck converter, in the LX, that what which we have been talking before.
Mm-hmm.
There we will be having this kind of current waveform.
Yes.
But in transformer they say always this current should drop to zero at the end of every cycle.
Yeah. So
Uh,
some of this part will be clarified in magnetic section where we will discuss about BH curve of the transformer. So generally a BH curve, if you see, let me just discuss a bit of it.
okay, sir.
So this is kind of BH curve, okay, and H is proportional to current and B is proportional to flux. Though this figure is not perfect, but this kind of BH curve you will generally see. So what happens when you are maintaining your current is equal to zero? It still at that point of time, your core has certain finite magnitude of flux. Okay, so if you can see from this graph, if you are coming at this zero value at origin, your flux has certain magnitude, right?
Okay.
And
Yes, sir.
if you are not maintaining DCM, then what is happening? This residual flux is keep getting added, right?
Yes, sir.
And this cumulative addition of the flux will lead to the saturation of your core. And after saturation, it will draw enormously high value of current, and then your devices may get damaged. So that is the reason that I try to answer a part of it. More of it we will see in the magnetic design. There you will get these all these regions clarified. Why BH, what is BH curve, what is happening in BH curve, those kind of things we will clarify, right?
Okay, sir.
Okay, so that's why basically it is a you know rough idea that why we always try to reduce current to zero level. Basically, we just do not want to bring it to zero level at time period t. we want to maintain this zero value certain time before the time period is getting completed. So we make sure that this magnetizing current is getting to the zero value before, way before the next cycle getting start. So this is what we want. I think this is not.
So if we keep the LM value less,
Hmm. Yeah.
then it is possible to
Then
bring down.
the slope of this curve ILM will be lesser. If you are sorry, if you are keep sorry, this slope will be higher. If you are having LM value of magnitude lower, then your slope will be higher.
Yes.
Yes, but still the point is same, that will it come to zero before the time period of the cycle, or will it exceed that point? So we have to maintain for any given condition this current should come zero before the completion of that time period. So why do you think reducing the value of magnetizing inductance will solve this problem?
Magnetizing, if I reduce LM,
Mm-hmm.
this slope will increase on time, and if I reduce the LS,
Mm-hmm. Yeah, yeah, go ahead, please.
increase the LX,
Yes.
then it will means come down faster.
Okay, so you are saying that
So we
if,
can ensure
huh,
that within the T time it will totally become zero.
okay. So you are saying if you increase the LX and reduce the LM,
Eh,
okay,
yes, yes.
then what statement did you use?
Then this problem we can solve. We can ensure that it will be this magnetizing current will be zero before
Will be
T ends
zero
within the time period,
before T.
so that residual magnetism will not be there.
Okay, so what is the reason behind this? I am not able to understand, but let us see what is happening when you are increasing Lx, then your slope of this load side inductor will be lesser and slope of the magnetizing inductance will be higher. And due
Uh,
to that, what happens? Let us see from this circuit.
Sir,
Yeah.
sir, you are saying some what problem you are referring to?
Uh, the problem is that we need to maintain ILM is equal to zero before the completion of that time period. Okay. So,
Yeah.
yeah, so he is saying that if we increase the inductance on the load side and we decrease the inductance of magnetizing branch, then our ILM should come down to zero before the completion of that time period. So we are
Sir, this
investigating.
one, this LX,
LX should also
LX,
increase, sir.
Huh,
Then
you
only it will come down faster.
then LM is coming, sorry,
LM, yeah,
the slope of ILM or LM would come down faster. That's what you are saying.
yes, sir.
Yeah, so we are observing the reason behind it, how LX and LM is related. So for that purpose, we will have to go back to the circuit. So here in this circuit, uh, if Lm is decreasing, then the slope of I3 will also fall fastly, and the slope of ILX. Okay, so see from this circuit, let me use see. So you said that LX we will increase, then then slope will look like something that, and it can be in CCM, right? Sorry, who asked this problem? Rakesh, were you?
Yes, sir.
Yeah, so it should be in CCM. That you agree?
Yes, yes.
Yeah, so it can be in CCMs. So if it is in CCM and ILX slope is like that, where V naught by Lx has been reduced since we have increased the Lx. Now this current is reflected on the tertiary terminal of the winding of the transformer. So I3 is equal to ILX into N2 by N3. So the magnitude of I3 based on ILX we have got, and after that ILM is equal to I3 into N3 by N1, right? So from this point, mm, since we have increased ILX, sorry, we have reduced ILX, peak value of ILX we have reduced, so our I3 should get reduced and ILM should be reduced. Okay, so the magnitude is, getting reduced, but the relationship between time of conduction, that is I am not able to observe between them.
Sir,
Yeah.
sir, this relation will not hold in off state, right? This I3 equal to ILX into N2 by N3 when the switch is off on the primary side.
Huh.
Uh, then this relation will not hold because I3 will IX will not flow through the transformer at that time. ILX,
Okay, you are saying that I3
ILX,
ILX
yeah,
ILX, yeah, could you repeat that?
ILX when the switch is off,
Mm-hmm.
this ILX won't be reflected into the primary because at that time the ILX will not flow through the secondary winding. It will
Hmm.
flow through the diode.
Yeah, yeah, but I have related it inductively. See, what is happening in primary winding when switch is off, this current through LM that is flowing through the primary turns, right?
The switch is off.
When switch is off, yeah, when switch is off, if you see, if you have kept it this direction of I1 and ILM is flowing like this, then I1 is equal to minus ILM. We can say,
Yeah, because sir, when the switch is off, this ILM won't flow actually. Through the diode only the current I3 only will carry the current.
yeah, yeah, that point
Because
related to that part, you are absolutely correct. But see, even when switch is getting off, whatever the current is stored, or sorry, whatever energy is stored, or whatever current is there, that will flow through this primary winding, right? It will keep flowing in the primary winding till the point all the energy has been exhausted. Don't you agree?
sir, actually that energy exhaustion is only taken care by this three, na, third
Yeah,
winding.
that's
LM won't.
yeah, that's you are correct. So whatever current is flowing here in primary winding, that is getting induced in tertiary.
Yes, yes.
Yeah, so
Inductively, yeah.
yeah, so whatever time this I3 is reverting back its energy to the source, till that time this ILM will be equal to minus I1. And once this transfer of energy back is finished, then ILM will be 0. So what is happening here in this slope? ILM is coming to the 0. After this point, ILM won't conduct. But during off state, see, this period is also off. But during this period, ILM is conducting, right? ILM has certain magnitude.
Yes.
So now do you agree or you still have some confusions?
Okay.
Okay?
Yes, sir.
Yeah. So I think magnitude wise it has a relationship with ILM and ILX, but
Sir,
uh,
actually, the
hmm,
center winding we have no, sir. We have drawn three windings.
yes,
The center one is the primary winding.
yes, yes.
Uh, so mm, the center one should carry the only the reflected current. It should not carry the discharge current.
No, no. See, this primary winding is connected to LM conductively, right?
Yes, sir.
Yes. So since it is directly connected to LM, so whatever current was flowing in the LM initially, that will still flow through the primary winding. LM and V1 is not connected inductively. Let me draw it once again so that,
Sir, actually,
uh,
in that case,
yeah, go ahead.
sir, in that case, if you see that diagram
Hmm.
which we have drawn,
Hmm.
the switch is opened actually. The switch is open at
Yeah,
that
so
time.
yeah, switch is open.
Both this LM and the primary winding are connected to the positive bus of the source.
Uh,
Then,
See, uh, let me redraw this circuit. Then I think it will be clear. It is quite a mess now, so that's why you might get confused. So see, this is the supply here. Okay, I don't think why this. This is LM. It
yeah,
is connected to primary winding.
yeah,
Okay,
yes,
in this manner,
okay.
and here you have switch,
Mm,
and this primary winding is connected inductively to the tertiary winding in this fashion, and we can call it N1 is to N2, and we have magnetizing inductance, and this is N1 terms. So after that, this,
Minister N3. Okay.
yeah, so right now I am drawing only for the off period where
Yes, sir.
confusion is there. Yeah, so let me remove this switch. Yeah. Now, when the switch is off, okay. Let me write N2.
Sir, why there are four windings?
Sorry, no, no, three windings are only there. This is magnetizing inductance. See, N1, N2, N3. And this is magnetizing
Okay,
inductance, so no four windings are there.
okay,
Okay. So,
yeah.
see, yeah, go ahead, please. If you have further.
Generally, LM we consider
Uh,
designated by primary only, that first winding.
uh-huh.
The inductance value of that is your LM.
Hmm. No, so you are saying that LM is associated inherently with our primary winding,
Yes,
which I turns off N1. Yeah, that you are
yes,
true.
sir.
You are correct. That is true. But the thing is that here we are trying to analyze and we have to play with magnetizing inductance. So we must, show the magnetizing inductance in this circuit. If you even show the approximate equivalent circuit of a transformer, an ideal transformer or any transformer, you will provide a separate magnetizing inductance, and that magnetizing inductance is the notation of the parameter how much magnetizing current or how much portion of the power is getting distributed in the process of magnetizing the core. So magnetizing inductance is an important parameter. We denote it separately in all kind of circuits. It is up to you. You if you want, you can eliminate it, but generally we show it. Okay. So it's all nothing but assumption. So in whatever way you want to
Okay, sir.
express, so it is that. Yeah.
Yeah, yeah.
Okay. So we were discussing that during off time, ILM at the instant of switch off, LM will have certain current that you can see from the graph as well. That when at the instant of DT, ILM is having certain magnitude, and that is the maximum magnitude, right? Peak value of magnetizing inductor current. So at the moment you disconnected the switch, this current will try to flow through the primary winding. Earlier what was happening, the current was coming from the switch or the source, okay? Some portion were flowing through the LM and some portion were flowing through the primary turns, and all were getting through the switch, and it was completing the loop in this fashion. Okay. Now it has not that option to flow in such a manner. Then what will happen? This ILM still have one path. Okay. So it will try to flow through the primary winding, and whatever current will flow here, ILM, and earlier I1 direction was like that and ILM was like that when switch was on. Now even when switch is off, the direction of I1, if you assume the similar to the condition when switch was on, then you can write I1 is equal to minus ILM. Okay. And this ILM, if you carefully observe, it is flowing in the primary terms of the transformer. This ILM can be induced with the turns ratio to the secondary winding. So if you see, and our dot convention is like that, so ILM and I2 is having relationship I2 into N2 by N1. So that's what I was saying. Do you have any doubt in this? TD, you have asked this question, so do you have any doubt in this?
Generally, sir, this LM is a part of primary winding.
Hmm.
So,
Hmm.
showing this current flow, how it will make a loop.
Okay.
because there is no separate component. This passive element is only one.
Hmm. You are saying that LM is collaborated with
Yeah, this is
anyone.
a part of this primary winding.
Yeah, yeah.
Yes.
So see,
So
in
we
in
cannot show this loop. We cannot show.
see in a transformer, you won't see this kind of any circuit, right? You will see just a
Yeah.
transformer. They are the way of representing a transformer, and in a transformer, we are representing that whatever ILM is flowing, we generally, let me, okay, so what would have been appropriate? First, we should have discussed the magnetic portion. Then we should have moved into this kind of circuit. So let me explain you a circuit of transformer. So in this fashion, our primary supply is there. Okay, then
Yeah.
a magnetizing inductance we draw.
Yes, sir.
We are ignoring all the leakages.
This is ideal.
Mhm.
Yeah. We cannot call it ideal as of now as long as LM is there. So LM is an indication of practical circuit, but we are just ignoring the
Yes.
leakage reactances and core resistance. So see, uh, if in an ideal transformer we do not need any amount of current to magnetize the core, what is generally you see as a steel core, right? So in
Yes.
to magnetize core, no need of IM. It means if,
Yes. So LM will be open type
yeah, so
in
LM
ideal
will
case.
be open. As soon as you
Yes.
have practical transformer, generally what we use, we need certain portion. Let us say this is I1. Okay. I think
Yes,
in
sir.
one class I showed that I1 has two component. One is
Yeah. Yes.
core or active component. One is core magnetizing component,
Yes.
and one is power delivering component. In
Yeah.
loose words, you can say. So basically, in official language or in IEEE standards, you say generally this is a reactive component
Yeah.
and this is a real component. Okay.
Yes.
So to have power factor is equal to 1, you just want to use only real component of current so that you do not need to supply any proportion of the supply current to magnetize the core. You know, whatever the current is getting invested in the process of magnetizing the core, that is getting anyway
Mm.
wasted, right? But that is not at
Mm.
all wasted since you are utilizing it in magnetizing the core. Without magnetizing, you cannot have the transfer of power from the primary terminals to the secondary terminal. So it is
Yes, sir.
necessary and but it should require sufficiently minimum amount of current such that your transformer get magnetized, and then once it is magnetized at the rated condition, then you have formed a channel kind of thing. Now from through that channel you can easily transfer the power from the primary terminal to the secondary terminal. Okay.
Yes. Yes.
So now I hope this point should be clear.
Okay.
Yeah. So we will go back to the point where we left off. Yeah. So we were discussing that. Okay. So you pointed out that if you increase the LX and reduce the LM, your ILM should come to the zero value before the completion of time period. But that kind of relationship we are not able to observe till now. We try to see there is relationship between ILX and ILM, but there is no relationship in terms of time duration. So for what time duration ILX will flow and for what time duration ILM will flow. So through this expression you can relate ILX and ILM, but I am not able to observe. If you go back after this session and if you are able to derive certain kind of things, then we can we can again take that point in the next session. Okay.
Sir,
Yeah.
uh, here ILM is equal to I3 plus N3 by N1. So if N3 is equal to N1, this I3 is equal to ILM. And if the ILM component at the when switch is on is going to be the same component delta ILM in
So,
the
so
off period, so
sorry,
that
sorry. I lost you in between. Could you repeat it in a slow manner? I will write it here. Okay.
okay, ILM
Yeah, yeah. ILM
is equal to
is equal to
I3 into N1
N3 by N1.
N3 by N1. Okay.
Yeah,
If N3 and N1 are equal,
yeah.
they're supposed to be,
Yeah.
then in the
Huh.
same delta T
Huh.
in off period will require
Hmm.
to I3 to get zero. Okay, slope will remains positive slope and negative slope of IL3.
Yeah, that is I am about to derive this point. So you are correct. You might have studied or you might have known it from earlier. That is I am about to derive. So I will derive what is the condition of relationship between N3 and N1 to get ILM is equal to 0 before the completion of time period. That's what you want?
Yes, that DT going
Y-
to be the same.
Yeah, yeah, yeah. That dt is same. So let me tell you that relation, then I think we will be on the same page. So that relationship is d into 1 plus n3 by n1 should be less than 1. Am I right?
Yes,
Yeah.
yes.
So that I am going to derive it and we will see that why that condition is appearing. So before that I want to take a 2 minute quick break. So if it is okay with you, and
Okay, sir.
yeah, okay, thank you.
Thank you.
So hi, I'm back. Let us start that derivation. So we will apply that slope of current in the magnetizing inductance. So and we will try to equalize slope of current in magnetizing inductance. Okay, so when switch was on, so dilm by dt was simply Vs by Lm. Okay, this can be considered as first equation. When switch was off, dilm by dt, what will be its value?
minus Vs by
Yeah, minus Vs by Lm. Sorry, minus Vs into N1 by N3, right? It is getting
that's
induced from the tertiary side.
yes.
Yeah,
And
into N1 by N3. I hope no problem till this point.
yes.
Yeah. So this can be considered as second equation. Okay. Now both should match with certain time. So this dt, let us write it as del ILM when switch was on. Del ILM was Vs by Lm into dt. Okay. Now del ILM of should be equal to minus Vs into N1 by N3 by Lm. It will have certain t. Okay, so we will take it as t2, a small t2. Okay, and we are stating that dt plus t2 is equal to t naught, where ILM is getting 0. So this instant t naught we are saying. Okay, now we can equalize both the expressions of del ILM. So when we do that, let me write, both should be 0. Del ILM on and del ILM off should be 0. And when you add del ILM on plus del ILM off, we will get certain relationship that will be Vs by Lm into dt plus, sorry, minus Vs into N1 by N3. Sorry, why it is Lx? It is Lm by Lm into T2 will be equal to 0. Okay. Now, if we take this term on right hand side, then Vs by Lm into dt will be equal to Vs into N1 by N3 by Lm into T2. and we can cancel out the Vs by Lm term from both the sides. Okay.
So T2 is a 1 minus dt,
T2 will be equal to
1 minus d into t.
Not
no, no, no,
necessary.
no. T2 will be N3 N3 by N1 into dt. No, N3 by
Yeah,
N1 into dt.
dt.
But in time, this turn ratio will not come into picture.
Sorry, could you please repeat that point? What you are saying?
In time, this there
T
won't be scaling of this uh,
Yeah, yeah.
and
Okay,
turn
so
ratio.
you are saying that T2 should not be dependent on N3 or N1 or ratio of turns
Yeah,
to
yeah,
N. Yeah.
yes,
So
sir.
why you are saying that?
Oh,
See,
because
okay,
it
okay.
should not affect time. No? Time is independent.
Yeah, time is independent, that you are correct, but this is the time fixed for the discharging of that inductor current, and that can be dependent on turns ratio. Why? Because if N3 is higher than N1, right, then the current flowing in the tertiary component will be for longer period compared to the primary period. So here in isolated DC-DC converters, all the manipulations and transfer functions are dependent on turns ratio. So from those
Yeah.
relationship, you can always infer that turns ratio are here playing a major role in all the parameters. So that's why it is
So,
reflected in time also. And from this time expression, if you equate the unit also, if you see the unit and dimensions, then it is on right hand side it is all again in second, and on left hand side it is also in second. So it is not violating any conditions.
but sir, this turn ratio effect you are taking in voltage term, no?
Yeah, but turns ratio come in voltage, current, everywhere, and this is just a
Yes.
manipulation of the equations. That what I am going to conclude after this derivation. That when this condition satisfies, then your magnetizing current will fall to zero quickly. Okay, and if you
Oh,
observe from the circuit as well, see from this circuit, if ILM has certain value and N1 is higher than N3. Okay, let us assume certain case. Let me write it, otherwise we will be confused. So, any clean circuit is there. Yeah, so let us suppose in this circuit, uh, N3 is higher than N1. Okay, and ILM equal to I I2, we can say that I2 current is flowing in N3, so ILM is equal to I2. Okay, then what will happen? Sorry, we should not write ILM equal to I2. So by considering only first condition, when N3 is greater than N1, now if you derive the relationship between ILM and I2, ILM by I2 during off condition, okay, what is the ratio of this ILM by I2?
N1 by
N2 by
N2, N3 by N1.
N3 by N1, right? So if the ratio of this turns ratio related to ILM by I2, then if I2 will have certain magnitude, then ILM will exceed, ILM will be increased value, right? So if you increase the N3 turns significantly, then your ILM will be much higher. Doesn't matter how much the magnitude of I2 is there. So since ILM is depending on turns ratio here, so that its decay period will also depend on that factor, turns ratio. So turns ratio is here a significant parameter that will influence so many things in the circuits.
so this ratio we are relation we are writing for discharge.
for off period, yes.
Okay.
Sir, this is ILM is
Hmm.
divided by I2.
Where?
This you are telling this ILM upon I2.
Huh.
So this should be it is equal to N3 upon N1.
ILM by I2 can be written as
ILM
N3 by N1. Yeah. And see, here I derived step by step. Okay. So if it is wrong, then during derivation it should have been reflected, right?
yeah.
I did not violate any condition during the derivation. If you see the derivation carefully after the completion of this session, then you will observe
Okay.
that there is no mistake in this derivation. Okay. Shall I go ahead?
Yes, sir.
Sir,
Huh. Yeah.
sir, this DINM by dt, which I
Hmm.
have written in off state.
Hmm.
Sir, this Vs should not be okay.
That is not
So
Vs.
here
That is voltage appearing across the tertiary winding. Okay, that is not a straight away Vs. That is the voltage appearing at tertiary winding transformed to the primary winding. See, from this circuit here, when the switch is off, the voltage here is nothing but minus Vs, right? Sorry, minus Vs. This voltage is getting induced to the N1, right? With the turns ratio of N1 by N3. You understood?
Yes, sir.
Yeah, so that's
sir
why I,
here
yeah,
this N3 is in secondary winding, no?
N3 is in, sorry, N3 is the turns of this tertiary winding and N2 is the turns of this, let me remove it
We
for,
have to correct I through I3 N3.
yeah, actually N2 I written
The
here.
tertiary should be in between, no?
Tertiary is at the same condition, that is correct. N2
Yeah.
just I wrote at different place, N2 should be here. Yeah.
Yeah, now it is okay. Yes, sir.
And the I2
Now
should
it
be
is.
I3.
No, no, I2 is I2. I2 is
I2.
I2. Yeah.
Yes, sir.
In this convention, I have written I2. If you want to write I3, you can write I3. Yeah.
Okay.
Ideally, in a
Now this yes.
yeah, in first circuit, I wrote I2 here and I3 here. But just to quick explanation, I wrote I2 here. So if I wrote I2 here, then I derived I2 accordingly. Okay. So these are just conventions, but the what matters is the derivation, and whatever you have taken the convention, you must be stick to that.
Okay.
So that's what we did, and with that derivation,
Sir, here your aim is to make T naught less than T.
yes, yes, that is the aim of our
Okay.
derivation. Yeah,
Less than or equal to T.
less than or equal to t. But generally we
Okay.
keep it less than t because of that VH curve explanation I gave. I will explain it once again. So T naught should be less than T.
Okay, sir.
Yeah. Okay, so T2 we derived that it is equal to N3 by N1 into dt. Okay, and T naught was dt plus T2. Okay, and this we are trying to keep it less than T. Okay, and we can further simplify it, dt plus N3 by N1 into dt should be less than
So
T.
dt plus T2. T is equal
Okay,
to
yes, 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 here T2 will be there. Thanks for pointing it out. It will be T2. Yeah. So we can take dt as a common factor 1 plus n3 by n1 less than t, and t will be cancelled. So the condition to get discontinuous conduction mode of magnetizing inductance should be such that d into 1 plus n3 by n1 should be less than 1, and d
Done.
is generally kept less than zero point 0.5. Okay, so that's why n3 is kept at n3 is generally kept at n3 is equal to n1. Okay, and d is zero point 0.5.
And is less than or equal to
Yeah,
1.5.
then your this expression will lead to less than 1. Any doubt in this? Okay, so if no
Yes, sir.
doubt,
In three, you have it is as the tertiary winding that central one. Na? This convention you have put.
N3 is the turns of tertiary winding where diode is connected
Yeah, yeah.
uh,
Yes, sir.
through freewheeling condition when switch is off. Yeah. So N3 is the turns of this winding. Okay. So the final thing is to identify the blocking capability of the switch. Okay. So switch voltage can be written as Vs minus, if you apply the KVL across the circuit, uh, so you will what you will get that I am writing, that will be Vs minus Vs into N1 by N3 when switch is on. So when switch is on, let me show you the circuit once more. When this switch is on, if you will see, yeah, then the voltage across the switch will be Vs minus Vs minus V1, right? You can see it as Vs is the polarity of Vs. If you apply this kind of KVL, it is Vs minus V1, okay, plus this V switch when the switch is on. And that will be your voltage capability of the switch. And V, when this, I think I have derived this point in last session also. Yeah, this is the point where I derived in the last session. V switch is equal to minus Vs minus V1, which resulted into minus Vs into 1 plus N1 by N3. And generally we keep N1 is equal to N3, then the switch blocking capability should be the twice of the supply voltage, right? And yeah, so and diode voltage blocking capability we already derived in the last session. So I think we are more or less finished with the concepts of flyback and forward converter. Finally, we will solve some problem now, one or two problem, so that we will be well versed with this concept.
That BH curve for this thing.
Huh.
That
Yeah, BH curve that I want it to explain in when I start magnetics. So as soon as I finish this forward converter, I I will try to start magnetics as soon as possible, and in that I will explain in detail. So I just explained here BH curve just because of the reason that one person asked that why we are keeping ILM equal to 0 before the starting of the next cycle. So I try to answer it from the BH curve approach. Do you have any doubt in this?
please explain. Repeat that one.
Yeah,
This
so what I told during this BH curve, actually this is not correct. It is like something. Yeah. So I was saying that when the current is going to the value 0, okay, when are bringing back the magnetizing current to the 0, our magnetic field intensity is becoming 0. However, residual magnetism or residual magnetic flux will be in the core, and that will have certain value. It is known as Br, right? And if we do not bring back to 0 value every time or way before the time period of that cycle, then what will happen? This flux will be added cumulatively and it will lead to the core, to the saturation,
saturation.
and after that it will demand enormous value of current. So that was my explanation for that reason.
So from this BS curve, means we have to uh, make negative ampere turns available to
Hmm.
make it zero.
Yes. So,
Means suppose for CRGO, BR is around zero point 0.6 Tesla.
huh,
Okay,
huh.
and it will so it will demand a certain amount of ampere turns to bring it to zero.
Yes, yes, in negative direction. You are right. So that's why
Yes, yes,
generally we operate core or transformers with AC supply, right? So there in AC
yes.
supply we have sinusoidal kind of supply, and
Hmm.
sinusoidal we know that it will be positive for half duration and negative for half duration. So
Yeah, this problem
it
won't occur.
yeah. So then in that case it will be in safe zone, right? But
Yes,
here
sir.
we are consistently applying only positive supply,
Yes.
and even though we are applying negative supply but in switching manner, so that's why we wanted to keep it 0. But if you see any electrical machines including transformer, you will see that flux will we want desirable flux in sinusoidal nature. Okay, so if flux is in sinusoidal, then only our EMF whatever will be induced, that will be sinusoidal with 90 degree of phase shift.
Hmm.
Okay, and hence if back EMF is sinusoidal, then E by R current will also be sinusoidal, so it will be overlapped with this kind of waveform. This is for I,
Yes.
this is for E, and this is for phi. So for ideal condition, we want this kind of curve, but we are not able to achieve with DC supply. So that's why we relied on switching of DC supply with the help of switches, and we tried to achieve, semi sinusoidal or semi kind of thing, whatever we try to achieve in AC kind of thing. Did that answer your question?
Yes.
Okay. So let me discuss one problem based on forward converter. Since we are at the verge of finishing forward converter, I wanted to wrap it up with a problem. Okay. So a supply voltage of 48 volt with load resistance of 10 ohm, Lx is equal to 2.4 millihenry, Lm is equal to 5 millihenry, capacitance value is given with 100 microfarad, frequency is 35 kilohertz, and turns ratio of N1 by N2 is 1.5, and turns ratio of N1 by N3, as we observed, that should be 1, and duty ratio also should be less than 0.5, so it is given as 0.4. Okay, so these are the parameters given. We need to find out the output voltage first. In first part we need to identify V naught. Okay, so V naught, we have derived with the volt second equation, that V naught is equal to V naught by Vs is equal to, just like buck converter, factor D into turns of output side divided by turns of input side, right? So when we will write it, plug all the values, and you will get 48 into D is zero point 0.4 into N2 by N1 is 1 by 1.5, right? So it will come out to be 48 into, so it will come out to be 12.8 volt. Okay, so far so good. Now in second part we are asked to compute maximum value in and minimum value in the load side inductance. I think some noise is coming. If you have no questions, could you please turn off your mic? Yeah, thank you. So in second part we are asked with ILX maximum and ILX minimum. Okay. So how to approach this with these given parameters? How to approach this kind of thing, ILX max and ILX mean? Any suggestion? Any approach?
So we need del IL, no?
Uh, we need del IL, that you are right. Let me write it. So ILX max will be equal to ILX average plus del ILX by 2. Now we have two parameters to compute. One is ILX average and one is del ILX. Okay. So with this much given parameter, how to proceed with ILX average computation and how to proceed with ripple in LX inductance.
So the average can be found from output voltage by R.
Perfect. So ILX can be written as V naught by R. Fine. Del ILX. Del
Is there
ILX.
any
Yeah.
assumption for 10 current ripple 10% or 5%?
No, no assumption is there. It is a straightforward problem where all the parameters are given. We just need to compute ILX max
using
in
L
that. Yeah.
using L and
ES
C.
divided by LX into del dt.
Vs divided by Lx into dt, you are saying?
Yes.
Yeah, that is correct in a way, but for forward converter, particularly during on period, the voltage across the inductance was V2 minus V naught, right?
Hmm.
And during the off period, the voltage was V naught only.
So it is V naught by L
V naught by Lx into 1 minus
into
d, right?
1 minus D. Yes.
Divided by f or into multiplied with t. So
Yes.
let me write it as 1 by t v naught into 1 minus d divided by Lx into t will be come into denominator as frequency, right? Any doubt in this step? So now I will plug in all those values. So V naught is 12.8 and R I think was 10 ohm. Okay. And
Yes, sir. Here
yeah,
uh, we are taking from output side and off period because VO is going to be constant rather than VS.
yes, yes.
That
That's
is one
what,
of the reason.
that is one reason, and another reason is we do not know V2 or calculation of V2 is a bit tedious, right? It is not a straightforward. We have to apply turns ratio. First, we need to know the Vs, then we will have to come to V2 with the turns ratio, right?
Yes.
So that's why we are taking the simplest path. So
Sim.
wherever minimum reluctance path, we will always try to take. Yeah. So I will plug half into V naught is 40 12.8 and D was zero point 0.4, so 1 minus zero point 0.4 divided by frequency and Lx. So the value of F is 35 kilohertz and Lx is zero point 0.4 millihenry. So 35 kilohertz into zero point 0.4 millihenry. So let me solve it. Parallelly, you can also try to solve this value. So first component is 1.28, that is straightforward, plus half into 12.8 2.6 divided by 35 into, so it is coming out to be 0.2742. So 0.274 I will take for simplicity. I hope this value should be correct. And overall, if I add with 1.28, I will get 1.554 ampere.
Yes, sir.
Yeah. So this is the magnitude of ILX max. Now since we have computed ILX max, then we should not have any issue in ILX mean. Okay. ILX mean will be equal to ILX average minus del ILX by 2. We computed both the components, that is 1.28 minus 0.274. Okay, it will come out to be 1.006 ampere. Okay, am I right?
Yes.
Okay, so that were the two part of this problem. Let us move to the third part. Okay, in third part we are asked to compute the peak current in the transformer primary winding. Okay, so what will be the peak current in the transformer primary winding?
Sir, it is
ILX max
VDC
into
into DTS by LM.
Sorry,
IL.
could you please
N3 upon N1.
uh, okay,
ILX max into N3 upon N1.
ILX max into nth. Let me write it whatever you are saying. So I1 peak should be ILX max
Into say that load side turns divided
into,
by N2 upon N1. Yes.
yeah, that is correct. And any other terms?
Plus Alex.
Uh,
LM.
Plus
LM.
LM,
ILM.
ILM max. You try to say
Yeah. ILM max.
ILM max. Okay, so I hope you are satisfied with this expression and it is correct as well.
yes, sir.
Yeah. So ILX max is 1.56 into N2 by N1 is 1.1 by 5, 1.5 plus ILM max. Have we computed ILM max?
No, sir.
Okay, so I haven't computed ILM max and ILM
Sir,
max
it is
can, yeah, go ahead please.
no, it is VDC into DTS by LM.
Yes, yes,
LM max.
it is quite a straightforward Vs into d by FL. So dVs by FLM I can write. Now further plugging all those values, this portion will be 1.56 divided by 1.5. It is 1.04 plus D was zero point 0.4, Vs is 48, F is 35 kilohertz, LM is,
So when this
sorry,
should be DVS upon because it is this it is peaking during
hmm,
the half cycle, half period only. Means,
hmm,
so
yes.
DVS.
See what I
Okay, you
have
have taken
written,
D.
yeah, yeah,
Okay.
what I have written here, Vs by FLM, sorry, Vs by LM, that is the slope magnitude, and
Yes, sir.
during
Into time.
dt. So this is the simplified
Okay,
version of
okay,
this.
okay, sir.
And Lm is 5 millihenry. So 5 into 10 raised to power minus 3. Okay, so if I will simplify this,
Sir,
yeah, go ahead, please.
this reflected current,
Huh?
it has to be N1 by N2, right?
Why you are saying so?
Because this is the reflected current from the secondary.
Yeah, see, that that condition applied to voltage only. In current, it gets reversed. So on which side this ILX is flowing, we will multiply with the turns of that side only, right? So ILX is flowing on the secondary side. So it will be multiplied with N2. You recall the concept of MMF. MMF is nothing but N into I. You got that point? N into I. So N2 into ILX max. N2 is the turns of the secondary side and ILX is flowing as well in the secondary side. N1 is the turns
Yes.
of primary side and I1 peak is flowing in the primary winding. So this is just the balance of MMF or power balance
Okay.
indirectly you can say. Yeah.
Sir, actually,
Hmm.
during the on time, only the secondary side current will flow through the secondary winding.
During the on period only it will flow. Yeah, fine.
So at that time, if we refer to if we see the reflected component of current in the primary,
Uh,
then it will be N2 by N1 into,
okay, okay. Do
sorry,
not get
N1 by N2 into I. Sorry,
oh,
just a minute.
okay, okay, okay. Do not get confused. Let me go back to the circuit.
Sir, it's correct only, sir.
Correct? Okay.
Yeah, convinced. Yeah.
So let me compute the second term. That is zero point 0.4 into 48.
0.11, sir.
0.11. Okay. I will take it as 0.11 and it will come out to be 1.15 ampere. Am I right? Yeah. So it is correct 1.15 ampere. Okay. I hope it is clear. Now moving to the last part of this problem. We need to verify, okay, this is verification related question. We need to verify that magnetizing current is becoming zero during each switching period. Okay, so we have to verify that ILM should become equal to zero. It indirectly means that magnetizing current should be resetted to the zero value during each switching period. So for this kind of problem only, particularly we have derived that certain condition. If you are able to recall, what was that condition? D into N1 by N3.
dt into 1 plus n3 by n1 should be less than 1.
Yeah. So that condition is nothing but D into 1 plus N3 by N1 should be less than 1. Okay. So we will plug all those values. D is zero point 0.4 into 1 plus n3 by n1. What was n1? N3 by n1 was 1 anyway. So it should be less than 1. And of course, zero point 0.4 into 2, that will be zero point 0.8 and that is less than 1. So it means core is getting resetted during each switching period. Okay. So it is satisfying that condition. And last part, in this part only, we have to compute that period, how much time it is taking to come back to zero after the switch is opened. Okay, so let me write it. Time taken by magnetizing current to return to the zero value. Okay, so what should be that time value? That should be t2, right? Recall that from that graph, we identified that t2 is that time that is taken by ILM to come to the zero value, and that time value we need to compute. So what is the value of t2? That was dt into n3 by n1, right? And we know d, we know frequency, so indirectly we know that t, and n3 by n1 is 1. So 0.4 into n3 by n1 is 1 divided by frequency, that is 35 kilohertz, and it will come out to be 11.4 microsecond. So in 11.4 microsecond, the value of magnetizing current should drop to 0. Okay, is it fine?
This is from DT, right, sir?
This is from dt. What dt?
No, no. From DT, it has to take 11.4 milliseconds to come to zero.
Yeah, this is dt 11.4, and n3 by n1 is anyway 1
No, 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 sir. This 11.4 millisecond, the
microsecond.
starting point of this the reduction is from DT, right?
Yes, 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 that is correct. From dt, yeah. And if you observe this value, that t2 value, that t2 is indirectly coming out to be dt, right? So whatever time it is getting to rise up from 0 to ILM, the same amount of time it is taking to fall back to the 0, if n3 by n1 is equal to 1, if it is 1. Now, as we increase the number of turns in tertiary winding, if you try to increase this ratio n3 higher than n1, then what will happen? Your magnetizing inductance might go in CCM mode. So that we always want to avoid. So simply, to maintain in discontinuous conduction mode of magnetizing inductance, just make sure N3 is equal to N1 and D is less than 0.5. That's all. Then your converter is, or magnetizing inductance of forward converter will be in DCM mode. Is it fine?
Yes, sir.
Great. So I think it's time to wind up the session. If there are any final questions, we will discuss that. And from the next,
Sorry,
yeah, go ahead, please.
in magnetics, are you going to discuss the magnetics for the DCM mode of and CCM mode of the forward as well as or flyback?
Uh, See, in magnetic section, what I intend to discuss is the uh, BH curve and inductance and permeance, reluctances, those kind of things, Ampere's law and Lenz's law. And once you know how to design inductance from those kind of parameters, then after that portion we have already discussed, right, from flyback and forward. Once you know how to get the value of that much inductance, then you are free to include those values of inductance in this kind of circuits. So actually the magnetics part is prequel to this DC-DC converter. You got my point?
Magnetics part is?
prequel to the DC-DC converter, isolated DC-DC converter. Ideally,
You
what
meant
should
us.
have happened, we generally study magnetics first, then we learn all those isolated converts, because we must have certain initial knowledge of transformers, inductance, permeance, reluctance, all related to magnetic design. But what happened that in this course structure, we started with DC-DC converters first, and then we are entering into basic magnetics. So that we what we are going to study, that will be prequel to this kind of thing. However, that is included in the course, so we must discuss those things.
Yes, sir.
Yeah. So from next session, we will start the magnetic section, and we will go ahead with that.
Thank you, sir.
Thank you very
Thank
much. Thank you very much, everyone.
good night, sir. Thank you.
Good night. Thank you.
Good night.
Good night.